So welcome to Electronics 6LA, and we are in PYQ of signal systems. In this lecture, we will see the signal systems question answers of fourth semester 2024 and 25. So we'll see all the short questions in this lectures. Okay. The first question is there define energy and power signal. Okay. So this is all 2 mark questions. So first question is there. You have to define the energy signal and power signal. Okay. So first of all, we will define what is energy signal. A signal is said to be energy signal if the energy is finite. Okay, so it should be finite. E is from 0 to infinity. So any value between 0 to infinity, it said to be finite. Okay. Similarly, the second condition is that for energy signal, the average power is always 0. Okay. So if the two conditions are met, then the signal is said to be energy signal. If the average, that is the average power equal to 0, average power equal to 0 and the energy is finite. Okay, so if these two conditions are met, then the signal is said to be energy signal. Okay, so for a discrete time signal, how to find out the energy? The energy can be found out as E equal to, this is the formula for finding out the energy of a discrete time signal, where x of n is a discrete time signal. Okay. Similarly, for power, for a continuous time signal, the energy of a continuous time signal, that is x of t, is defined as E equal to limit t tends to infinity minus t to t x of t whole square dt. This is how we can find out the uh, energy of a discrete time and continuous time signal. Okay, let us see some examples of discrete time or a continuous time energy signal. This is the x of n equal to 1 upon 3 to the power of n u of n. This is a discrete time energy signal. Okay, similarly, x of t equal to e to the power minus 3t u of t. This is a continuous time energy signal. Okay. So next is a power signal. So a signal is said to be, power signal is the average power that is finite, and in this case the for power signal the energy is always infinity. Okay. So if these two conditions are met, that is called the power signal. So if E equal to infinity and the average power is between 0 to infinity, then it is said to be a power signal. Okay. So the for discrete time signal, the average power of a signal x of n is defined as, this is the formula for finding out the average power of a discrete time signal. Okay. Similarly, for continuous time signal, this is the formula for finding out the power in case of a continuous time signal. So x of t is a continuous time signal. Okay. So now let us see some examples of continuous time and discrete time power signal. Okay. So these are the discrete time signals which are called as the power signals. Okay. Now this is x of t equal to cos t. This is a continuous time power signal. Okay. So these are some examples of power signal. Okay. So this is our first question. The second question is that write down the condition of stability of a discrete time. This is discrete time LTI system with respect to the positions of poles. Okay. For discrete time, that is the linear time invariant system, is stable if all the poles of the system function, that is, lie inside the unit circle. Okay, so all the poles that should be inside the unit circle to have the stable systems. So for this condition, this is the PK, PQ are the poles. Okay, so that should be less than 1. Okay, the poles should be less than 1. So where PK are the poles. So you can see for any discrete time LTI system is said to be stable if this poles, you can see the unit circle. Okay, lies, the poles will be lies means less than 1. Okay, so suppose this is the unit circle, the radius is 1, the poles should be lies uh, that is the inside this unit circle. Okay, to have the stable system. Okay, so this is how you can tell the system is stable or not, depending upon the poles. If the poles lie inside this unit circle, then it is a stable system. Okay. So then the third question is that it is the Parseval's theorem. Okay, for uh, continuous time Fourier transform. Okay. So the Parseval's relation state that the energy in time domain is equal to the energy in the this frequency domain. Okay. So this is the Parseval's relation. So this is actually energy of that continuous time signal x of t. Okay. So this is called the energy of continuous time signal x of t. Okay. If the energy in this it is how to find out the energy of a continuous time signal. Okay, it should be 1 upon 2 pi. That is the in the frequency domain. This is the formula. So energy formula. So this should be equal. Okay. So the Parseval theorem states that the energy in the time domain is the energy in the time domain is equal to the energy in the frequency domain. Okay. So if the Fourier transform of x of t continuous time signal is x of j omega, then energy of x of t its Fourier transform would be 1 upon 2 pi minus infinity plus infinity x of j omega square d omega. So this is called the Parseval's actually energy theorem also. Okay. So this is our third question. The fourth question is that state and prove the time holding properties of Z transform. Okay. Actually, this is not in the course of signal system, the Z transform. Okay. Anyway, so this time holding means it is the time reversal property. Okay. So time reversal property you have to state and prove also. Okay. So that is how is that you can see. So if x of t, the Z transform is x of z, okay, then x of minus n. The time reversal property says that what is the Z transform of x of minus n? It is x of z inverse. Okay, so this is the time reversal or time folding property. Okay, of Z transform. Okay, so let us prove that. So what is the Z transform formula? So how to find out the Z transform? So Z transform of a that is the discrete time signal will be summation of n is minus infinity to plus infinity, that is x of n z to the power of minus n. Okay, so we need to find out the z transform of x of minus n, so that would be x of minus n z to the power of minus n. Okay, let us take l equal to minus n, so let us put over here. So l equal to from minus infinity to plus infinity, so x of l, that is z to the power minus 1 to the power of l. So we can write this is here actually z transform of, that is the z to the power minus 1. Okay, so this is how you can prove the means time holding property or time reversal property of the z transform. Okay, next question is that write the trigonometric form of Fourier series. Okay, so you can see this is the continuous time Fourier series. Actually, Fourier series can be applied to the periodic time signals only. Okay, so the signal x of t is periodic with time period t can be represented as actually any periodic signal that is x of t can be represented in the infinite sum of cosines and sine harmonics. Okay, so let us see that. So this is our trigonometric form of Fourier series. So x of t equal to a0 by 2 summation of n cos and n omega t plus bn sin omega t. So what is this a0 by 2? Actually, this is called the DC component. Okay, this a0 by t is the DC component. Okay, it is the average or mean value of the signal over a time period. Okay, similarly, it is a n cos of n omega t. So this is the amplitude and frequency of the cosine harmonic. Similarly, bn sin n omega t, it is the amplitude and cosine means amplitude and frequency of the sine harmonic. Okay, so how to find out a0? So a0 equal to, you can see it is the DC component or average value of the signal over a time period. So it can be found out by 2 upon t 0 to x of t dt. Similarly, how to find out an? This is the formula for finding out the n. Okay. Similarly, how to find out bn? So this is how you can find out bn. Okay. So you have to mention all this in your answer sheet. Okay. So this is the trigonometric form of Fourier series. Please remember that the Fourier series can be applied to the periodic signals only. Okay. The next question is if x of n equal to 19.8, find its DFT. This DFT means discrete Fourier transform. Okay. So this is the formula for finding out the discrete Fourier transform of a discrete time signal. Okay. So where k is from 0 to n minus 1. Here you can see in this case the n is capital N equal to 2. Okay. So number of samples. Capital N is the number of samples which is 2. So let us put here. So k will be from k equal to 0 and n minus 1. So it will be 1. So two values you can put. We can put k equal to 0 and we can put k equal to 1. So we can find out what is x of 0 and x of 1. Okay. So let us find out. So what is x of 0? So x of 0 you can see that is the x of 0. So k equal to 0. So k, if we put here the k equal to 0, it will be e to the power of 0. If you can put k equal to 0 over here, so it will be e to the 0. So that will be 1. So now it will be that will be x of 0 plus x of 1. Okay. So what is x of 0? X of 0 equal to 19 and x of 1 equal to 8. So it will be 27. Okay. So next question is my next thing is the x of 1. So you have to find out x of 1. So it is 0 to n minus 1, n equal to 2. So it will be 0 to 1 x of n e to the power minus j by this k value is here 1. Okay, k value is 1 and capital N equal to 2. So it will be minus j that 2 pi n divided by 2. So now this 2 get cancelled out. Okay, so we have actually you can put the values of n equal to 0 and n equal to 1. Okay, so now if we put n equal to 0, it will be x of 0, so e to the power 0, it will be 1. If we put x of 1, that will be e to the power of minus j pi. Okay, so let us put the Euler's formula. So it will be x of 0 equal to 19, x of 1 equal to 8, so it will be cos pi minus j sin pi. Okay, so now what is the value of means sin pi? It will be 0 and cos pi equal to minus 1, so it will be 19 minus of 8, so it will be 11. Okay, so we have found out our x of k. Okay, so it would be 27 and 11. Okay, so next question is here. So what is aliasing? Okay, so aliasing means, so it is a distortion. Okay, so if the signal is sampled below the Nyquist rate, okay, so what is Nyquist rate? Nyquist rate equal to that is sampling rate is should be twice of fm. So if this fs is less than twice of fm, so that should be distortion occur. That distortion is known as your aliasing. Okay, that means the overlapping of frequency components. You can see if fs is here less than twice fm. So Nyquist rate equal to fs is equal to twice fm. If the signal is sampled less than twice fm, then there will be a overlapping of frequency components. Okay, so if fs is less than twice of fm, the frequency component will overlap and hence the original signal cannot be recovered from the sampled signal. Okay, so that is the called the distortion, or you can see the diagram. So you can see over here, this is our, I mean this is the sample signal actually. This is the frequency spectrum of a sample signal. Okay, this is the frequency spectrum of a sample signal. So you can see there is a two bands are overlapping. Okay, this due to this aliasing. So these two bands are overlapping here also. So this is called the distortion. Okay, this that distortion is known as aliasing. Due to this, the signal cannot be recovered. Okay, so in this case, the two spectrum you can overlap. Okay, so now how aliasing occurs if the signal is not band limited to the finite range. The signal should be band limited. Okay, to a finite range. Second one is that the sampling frequency is too low. That is the fs is less than twice of fm. Okay, that is the sampling frequency is too low. Okay, so now how to avoid the aliasing? The aliasing can be avoided by the signal can be should be band limited. So it can be assured by using the anti-aliasing filter before the sampler. Okay, so that x of t should be band limited. Okay. So band limited means no frequency will be, if this is the signal, this is the frequency spectrum of x of omega suppose. So this is minus omega m to omega m. So this is the, beyond this the frequency is 0. You can see the beyond this the frequency is 0. So that is the thing, it is known as a band limited. The signal should be band limited to a means above this omega m or below this minus omega m, the frequency equal to this omega m equal to 0. Okay. So the x of t should be band limited. That is can be done by the using the anti-aliasing filter before the sampler. Okay. This fs should be greater than equal to twice fm. So that should be greater than the Nyquist rate. Okay. The to avoid the aliasing. Okay. Next is here, state the sampling theorem. Okay, sampling theorem states that a band limited signal. I have told you what is band limited signal now. So a band limited signal of finite energy, which is no frequency component higher than fm hertz. That I have told you that no frequency components that higher than this signal. Okay, uh, then it can be described completely by its the sample values taken at uniform intervals that equal to 1 upon twice fm. Okay, that is the sampling period that should be get less than equal to 1 upon twice fm. Okay. Second thing is that the continuous times band limited signal of finite energy can be reconstructed exactly from its samples in the sampling frequency is at least twice of the maximum frequency of the signal. You can see fs is should be greater than or equal to twice of fn. Okay, to be there, we can in this, if we sample this signal above the twice fm, we can reconstruct the original signal. Okay, without any aliasing or without any data will be lost. Okay, so this is called the sampling theorem. Okay, next is calculate the sampling frequency of this signal. Okay, so let us see, this signal is divided into two parts. So it is omega 1, this is omega 1. So omega 1 equal to 150. You can see this is omega 1. So omega 1 t. So this is our a cos, the signal is a cos omega 1 t plus b cos omega 2 t. Okay, so now this omega 1 equal to 150. Okay, radian per second. So f equal to omega equal to 2 pi f of 1, omega 1 equal to 2 pi f 1. So f1 equal to 150 by 2 pi. So it is 23.87. Similarly, what is omega 2? Omega t equal to 450. So 450 means you have to find out f of 2, f2. So what will be f2? F2 equal to this 450 by upon 2 pi. So it is 71.63 hertz. Okay. So at this two, that is the, you can take the maximum of these two frequencies. What is the f max? It will be 142.26. So f max equal to maximum between f1 and f2. Okay, so maximum frequency between f1 and f2. So f2 is having the maximum frequency. So just multiply. This is the liquid sampling frequency. So it is 2 into fm. Fs equal to 2is into fm is the liquid sampling frequency. Okay, so it will be this one. Okay, this is how you can calculate the sampling frequency. Okay, so last question is that what is the difference between the recursive system and non-recursive systems. Okay, so let us take that recursive versus non-recursive system. You can see a recursive system, that is the one whose output y of n at any time n depends upon the past output values and also the present and past input values. Okay, so it depends on the past output values and also the present and past input samples. Similarly, this output of a non-recursive system, it does not depend upon the past output values, but it will depend upon the present and past input. So it will depend upon the present and past input, but it does not depend upon the past output. Then it is called the non-recursive systems. Okay. So you can see the examples. So it is a function of y of n minus 1. So this is the past output values. These are the past output values. Okay, so similarly, this is the present input values. These are the past input values. Similarly, in case of non-recursive system, these are the present input values. Okay, you can see past input values, but it does not depend upon the past output values. Okay, next one is this for LTI system. This is the means y of n. For LTI system, in case of non-recursive system, this is our y of n. Okay. So recursive system has the infinite impulse response. Similarly, a non-recursive system has the finite impulse response. Okay. So it is used in audio processing and telecommunication equalizations, and it is used in the digital filters in communications. So recursive systems, you can have the careful design to have the stability, but in case of non-recursive system, these are always stable systems. Okay. So these are the all the means this is a 2-mark question actually. I told you this is a 2-mark question. Okay, this is a 2-mark question. So these are the all the 10 means short questions. Okay. So in the next video we'll see some 6-mark questions relating to this signal system or semester 2024-25. So these are reference. Okay. So if you have any doubt, you can click to ask me in the comment section. Okay. So thank you all. Have a nice day. Thank you.